Hi everyone, David Pecker here, and in this video I want to discuss Newton's laws of motion. These laws govern the motion of objects, such as apples falling from trees, spacecraft and satellites orbiting the Earth, and the motion of the planets around the Sun. Now, before proceeding to describe these laws in detail, I want to remark that these laws are approximate laws, and they work well for low speeds and masses. It turns out that for high precision tracking of spacecraft, it is actually important to take into account relativistic corrections. That is, corrections due to both special and general theory of relativity. And the same is true for the planets. In fact, the precession of the orbit of Mercury was one of the tests of general relativity that we discussed earlier. Now, because the planets and our Sun are not super dense or supermassive objects, the relativistic corrections are rather small. On the other hand, if we wish to describe the motion of matter around super dense and supermassive objects like black holes, we must abandon Newton's theory and use general relativity, as this case we know is well outside of the limits of applicability of Newton's theory. Having established the limits of validity of Newton's theory, let's go ahead and start by discussing Isaac Newton himself. Sir Isaac Newton lived from 1643 to 1727. He was a brilliant scientist, having made major contributions to a bunch of fields, from optics to mechanics to fluid dynamics. Oh, and by the way, Isaac Newton also invented the first reflecting telescope. To show the power of Newton's intellect, let's quickly discuss telescopes. Telescopes first appeared in the Netherlands in the early 1600s. In 1609, Galileo Galilei learned about telescopes and started constructing his own versions and refining the designs. These refinements increased the magnification factor from 3x of the early military spyglasses to 23x, a telescope which Galileo used to discover the moons of Jupiter. Johannes Kepler further refined the design of the refracting telescope by using two concave mirrors instead of one concave mirror and one convex mirror. All of these early telescopes relied on light going through lenses in order to focus the light. The bending of light by glass is called refraction, and therefore all of these telescopes are called refracting telescopes. Because of the way they focus the light, all of these refracting telescopes suffer from the same problem, which is chromatic aberration. What is chromatic aberration? Just like a prism can spread out the colors of the light, so does a lens when it focuses the light. Light of different colors gets focused to different points. So the blue light in this diagram gets focused closer to the lens, while the red light gets focused further from the lens. Which means that a telescope using lenses cannot focus all the colors of the light simultaneously to make a sharp image. How does this affect image quality in real life? Well, here is a cool picture from Wikipedia showing a photograph of a pendant. If you look at the dangly bits at the bottom of the image, you see that they are colored purple, while the faraway part of the image is colored green. This is a typical chromatic aberration which is seen in photographs. Newton, having realized that chromatic aberration occurs in telescopes, decided to fix the problem. And how did he fix it? Well, instead of using lenses to focus light, he decided to use mirrors. Now, a mirror reflects light in the same direction, regardless of the color of the light. And hence, a telescope using mirrors or a reflecting telescope does not suffer at all from chromatic aberration. And indeed, this is exactly how we build telescopes nowadays. The image shows a schematic picture of the Keck telescope. The Keck telescope has three mirrors, a 36-segment primary mirror, which is 10 meters in diameter, then a secondary mirror and a tertiary mirror, which sends the light into the camera. Indeed, the significant contributions of Newton to science make him the #1 ranked scientist of all times, even above the #2 ranked scientist, Albert Einstein. Or at least, that is what a survey conducted in 1999 by the website PhysicsWeb tells us. Isaac Newton was also a great mathematician, having co-invented calculus with Leibniz. And of course, calculus is the set of mathematical tools which greatly help us in physics and also engineering, doing things like calculations of rocket trajectories. But don't worry, in this class we will try at all costs to avoid using calculus and instead just focus on the outcomes. Throughout his life, Newton was also interested in alchemy, that is, trying to turn lead into gold. Of course, he was not successful in that pursuit. Newton also studied theology, and he had his own perspective on the Holy Trinity, and therefore he viewed that worshipping Christ as God is idolatry. Fortunately, he was smart enough to keep his views to himself. Newton also participated in politics as a member of parliament and then a warden and a master of the Royal Mint. For his troubles, he was knighted, but of course not the fighting kind of knight. Newton was also elected the president of the Royal Society, which is basically the National Academy of Sciences in the UK. And it seems that Newton was also quite a bit of an arse. For example, as the president of the Royal Society, he had the society disparage Leibniz, the co-inventor of calculus, giving precedence to English science. Now, having a bit of idea of what kind of person Newton was, and also of his achievements, let's go ahead and discuss his laws of motion, starting with Newton's first law. Newton's first law states that objects at rest stay at rest, and objects in motion continue moving at a constant velocity, unless acted upon by a net unbalanced external forces. Now, our everyday experience says that Newton's law is wrong. It says that objects tend to slow down. For example, if I slide my keys across the table, they tend to slow down and stop. But that is because there are unbalanced external forces acting on the keys, and those are the forces of friction. Let's consider a thought experiment in which we minimize the frictional forces. That is, we're going to replace the keys by a hovercraft, which we can think of as a minimal friction device. Now let me start out by drawing the surface of the table, and on top of the table I'm going to draw the hovercraft. Now hovercrafts work by taking air from above the craft and forcing it out through the bottom, creating a cushion of air under the craft, allowing it to float in the air without touching the surface of the table. Now, what are the forces acting on the hovercraft? Well, first there is a force of gravity, which tends to pull the hovercraft down, and counteracting the force of gravity, there is the force of air pressure, which tends to lift up the hovercraft. Now, because the hovercraft is not moving, the net forces on the hovercraft must be balanced. That is, adding up the vectors for the force of gravity, F gravity, and the force of the air pressure, F air pressure, we get a net zero vector. Now, if the hovercraft is initially at rest, it will remain at rest. On the other hand, if it's initially moving, it will keep moving in a straight line until it slides off the table. Now let's ask the question. Suppose the hovercraft is initially at rest, and we go ahead and move the table under the hovercraft in the direction due east. Will the hovercraft remain stationary or will it move? Because we are not imparting a force on the hovercraft by moving the table underneath it, the hovercraft should remain stationary and hence not move. Now suppose that we want to make the hovercraft move. How do we generate net unbalanced force? Well, we have to push it, for example, with a stick. Newton's second law is a formula which reads F equals ma, or force is equal to mass times acceleration. To decode this formula, we need to understand what exactly is acceleration and what is force. So let's go ahead and start by asking the question, what is acceleration? Acceleration measures how fast velocity is changing. Suppose we have an object which at time t1 is moving at the velocity v of t1 equals to v1, and at time t2 it is moving at velocity v of t2 which is equal to v2. Now, how much acceleration is the object undergoing? Well, we have to divide the change in velocity by the change in time. The change of velocity is v of t2 minus v of t1, and the change in time is t2 minus t1. So let's look at the numerator of the acceleration formula. And oops, I forgot to put the vector symbols everywhere. So let's put those back. Now looking back, the top of the acceleration formula corresponds to the change in velocity, the final velocity minus the initial velocity, and the bottom of the acceleration formula corresponds to the change in time, the final time minus the initial time. Now we can rewrite this formula as delta v divided by delta t, where delta v corresponds to the change in velocity and delta t to the change in time. Now what are the units of acceleration? Well, acceleration has units of velocity divided by time, or meters per second divided by seconds, which is equivalent to meters per second squared. Now we come to the second part. What is force? Force is a measure of how strongly an object is being pushed. What are the units of force? Well, force, according to Newton's second law, is mass times acceleration. Mass is measured in kilograms, and acceleration, as we just saw, is measured in meters per second squared, and therefore the units of force are kilograms meters per second squared. This unit is usually called newtons, and the abbreviation for newtons is a capital letter N. Now, in order to see how Newton's second law works, let's consider accelerating hovercraft. So here again I draw a table, and on top of the table are two hovercraft. Hovercraft 1 has a mass of 1 kilogram, and hovercraft 2 has a mass of 2 kilograms. Both hovercrafts are pushed by a force of 1 Newton. Now let's go ahead and ask the question, how fast are the two hovercraft accelerating? We start with hovercraft 1. Manipulating Newton's second law, we get the formula that acceleration is equal to force divided by mass. From the diagram, we see that the force is 1 Newton and the mass is 1 kilogram. Now remember that acceleration and also force are vectors, and therefore we have to specify in which direction they point, and instead of representing the acceleration in component form, we just specify the direction in which it points, and that is to the right. Next, we aim to simplify units, and we do that by remembering that 1 Newton is equal to 1 kilogram meter per second squared. Now, bringing the denominator in as a fraction, we get 1 kilogram meter per second squared times 1 divided by 1 kilogram, of course still acting to the right. Now we notice that we have a kilogram in both the numerator and the denominator, and hence we can cancel these units. And what remains is 1 meter per second squared to the right. And this is the acceleration of hovercraft 1. To complete the calculation, we check our units. Are the units of acceleration indeed the units of acceleration? Looking back in the video, we verify that the units are indeed correct. Performing the same set of calculations for hovercraft 2, we get acceleration is equal to force divided by mass, and this time the force is still 1 Newton, but the mass is 2 kilograms, and therefore we get the acceleration of 0.5 meters per second squared, and again to the right. Now comparing the two hovercraft, we see that the more massive hovercraft accelerates slower when the same force is applied, and this makes sense. In order to make it accelerate the same, we have to push harder. Now suppose both hovercraft start at rest at time t equals 0 seconds. Now let's ask the question, how fast will the two hovercraft be moving after 10 seconds? Let's start with hovercraft 1. Now we remember that acceleration is the change of velocity, delta v, divided by the change in time, delta t. Now delta v is equal to the velocity at time t equals 10 seconds minus velocity at time t equals 0, which itself is 0. And that is all going to be equal to acceleration times the change in time delta t. Plugging in the acceleration, 1 meter per second squared to the right, and the change in time, 10 seconds, we can cancel the seconds in the numerator and denominator to get the delta v, or the velocity at the end of 10 seconds, is going to be 10 meters per second to the right. Following the same steps for hovercraft 2, delta v is going to be acceleration times delta t, plugging in the acceleration of a half meter per second squared and delta t of 10 seconds, and again to the right, we get that delta v is 5 meters per second to the right. Comparing these two results, we see that the heavier hovercraft 2, is accelerating slower, and therefore after 10 seconds of acceleration, it is also moving slower than hovercraft 1, 10 meters per second as compared to 5 meters per second. And finally, we come to Newton's third and last law of motion. Consider two objects, object 1 and object 2. For the purposes of this example, object 1 is going to be a hovercraft, and object 2 is going to be a stick that pushes on the hovercraft. Now, what does Newton's third law state? It states for every force F21, that is, a force that object 2 exerts on object 1, in this case the force that the stick is pushing onto the hovercraft, there is a force F12 that object 1 exerts on object 2, which is equal to minus F21. That is, there is a force from object 1's hovercraft that is being exerted on the stick, and it is opposite of the force that the stick exerts on the hovercraft. The pair of forces F21 and F12 are called third law pairs. These are forces which are equal in magnitude and act in opposite directions. Now, you might have heard of Newton's third law stated in the way that for every action there is an equal and opposite reaction. I personally don't super like this way of stating Newton's law for two reasons. So this way of stating Newton's law is less helpful. First, because what does action and reaction, which sounds like something that people would do, have to do anything with forces? And second, the fact that there is a reaction sounds like the reaction occurs after the action takes place. But forces in a third law pair are simultaneous. At this point, we conclude our introduction to Newton's three laws of motion. Now, while the three laws sound pretty straightforward, applying them is not so straightforward. Indeed, these are deep concepts which takes a while to practice to learn how to use. And this is exactly what we're going to do over the next several lectures and also homework assignments, with a focus on application of these laws to spaceflight. Thank you for watching, and remember to stay curious.